So let's take a look at log equations. So on the second page of those guided notes, you have a few different types of log equations of some different styles. So the first example, example 3 here, we've got more than one natural log. We've got natural logs that are on one side of the equation, or natural logs, or logs, I should say, not just natural logs, logs that are on each side of the equation. So the first one here, what I would do is probably go ahead and move that natural log of 3 to the other side. So I'm going to add the natural log of 3 to the other side. Cross that out. So we have natural log of x equals natural log of 3. Now, it's easy to overthink this. Don't overthink this. This is a one-to-one correspondence. Think about this. If I've got natural log of something equals natural log of 3, then what has to be the deal with the two things inside of the natural log? They both have to be equal. So it's like a one-to-one correspondence because I've got logs on both sides. I'm going to drop the logs and just say that x equals 3, and that's our answer. The next one is very similar. We've got log base 3 of 5x minus 1 equals log base 3 of x plus 7. It looks more complicated, but again, don't overthink this. We've just got log of this expression equals log of this expression. As long as the bases are the same, in this case they're both 3, then what's inside the logs has to match up again. So I'm going to drop the logs and I'm going to say 5x minus 1 equals x plus 7. I'm going to solve the equation from there. So I need to get the x's on one side. Let's subtract the x. So I get 4x minus 1 equals 7. Add 1 to both sides, and I get 4x equals 8. Divide by 4, and I get a value for x of x equals 2. Now, one sort of caveat with these log equations, if you remember back to, I think it was 4.2 or 4.3, we talked about the domain of a logarithm, that you can't take the domain, or I'm sorry, you can't take the log of a negative number. So whatever ends up inside these log expressions, whatever ends up on the inside, it has to be some sort of positive value. Every once in a while, when you work out an equation and you solve it, you'll get a number on the inside that produces, or you'll get a number that when you plug it in, produces a negative on the inside of the log. So just kind of double check your answers and make sure that they don't happen to give you a negative on the inside of the log. In other words, if you take that 2 and you plug it in, we would get 5 times 2, which is 10, minus 1, which is 9. So we're okay because that's a positive number. Over here, we would get 2 plus 7. Again, that's 9. It should be because they should be the same. So both of those, the 2 resulted in a positive number inside the logs. So we're okay there. We're going to see an example in a couple minutes where that's not going to work out quite as nicely. Let's try this one. We've got natural log of x minus 2 equals natural log of 2x minus 3. I'm sorry, plus natural log of 2x minus 3 equals 2 times the natural log of x squared. If you have more than one log on one side of the equation and you've got something, another log or something else on the other side of the equation, let's go ahead and condense our logs first. So remember that when we add logs together to condense, what property are we going to use? We're going to condense this into a single log and use multiplication. So we're going to have the natural log of x minus 2 times 2x minus 3. And that equals, let's condense on the other side. Remember the power rule. When you have a coefficient in the front of the log, you can move it back to the exponent position. So that gives you natural log of x to the second power. Now we're kind of back to the same situation we had in the last two examples, right? I've got log of something equals log of something. So what can I do with the insides of the two logs? It's not a very pretty equation, but this entire left side, everything inside that log, I can set equal to what's in the log on the other side. What's inside has to be equal. So we're going to drop the logs and say x minus 2 times 2x minus 3 equals x squared. And then let's FOIL that left side so we can see about factoring and using the zero product property. We're going to get 2x squared minus 3x minus 4x plus 6 equals to x squared. We need to get all the x squareds to one side and set it equal to 0. So I would go ahead and move the x squared to the left side. Let's come over here and write it. So then we have x squared. You notice that I had a negative 3x and a negative 4x. So that gives me negative 7x plus 6 equals 0. Now take a minute, and if you need to pause the video, solve that equation by factoring. You won't get anything that doesn't factor in this section. And this is no exception. So we've got x and x, a minus 6 and a minus 1 equals 0. So we set both of those equal to 0 using the zero product property. We get a solution of x equals 6 and x equals 1. Now, here's where you need to really make sure, especially when you have two solutions, that neither of these solutions, when you plug them into the original equation, will give you a negative or a 0 for that matter inside the log. Remember, we can only take the log of positive numbers. So let's start with x equals 6. Let's just check this. So if I plug in x equals 6 into this original equation, I get 6 minus 2. Is that a positive number? Yes, it is, so we're okay. 2 times 6 minus 3, is that a positive number? Yes, so we're okay. And if I plug in 6 into x, I just get 6. We're okay there. How about 1? So 6 was okay. How about 1? If we plug in 1 to this first little expression, what happens? We get 1 minus 2. Is that a positive number? No, it is not. So the 1, we're going to throw that out. It's not actually a solution because when we plug in 1, it gives us a negative inside the argument of the logarithm, and we can't have that. So our only solution is x equals 6. This is a good time to check these. Usually when we have a problem, it's going to be when we have this two-solution case. Oftentimes one works and one doesn't. Sometimes they both work, but sometimes one doesn't, and that's when you want to check it. Make sure. Okay, example 4, it says solve each logarithmic equation for x by isolating the log and switching to exponential form. So what I want you to notice about this example is we've got a log on one side, but we have a number on the other side. We haven't seen that yet in any of our other equations. And all of these equations, even after we condensed, we had a log on both sides, a log on both sides, a log on both sides. So when we had a log on both sides, we could drop the logs and set the insides equal. This time we have a log equal to a number. And so when that happens, we're going to have to switch it to exponential form. So what is the base when we're dealing with natural log? Don't forget that's an implied base e. So we switch it to exponential form. We're going to have e raised to the negative third power equals x, equals what's inside the log. We could leave it like that. We could write it as 1 over e to the third if we wanted an exact answer. If we needed a decimal answer for it, then we would just go to our calculator and we could do second e. So let me make sure you see this. The e key is right above the natural log key. In my calculator, I have to hit the shift or the second key. So I've got e to the negative third power, and I get about 0.0497. So I'll just round it and say 0.05. Okay. How about the next question? We need to get the log by itself before we do anything. So I'm going to subtract 5. So I have 2 times the natural log of x equals negative 1. And then I'm going to divide by 2. So I have the natural log of x equals negative 1/2. And same as the last problem, once you get it down to where you have a log equals a number, you want to switch it to exponential form. So the base for this is e again, so it's going to be e to the negative 1/2 power equals x. And you could leave your answer like that. You could get a decimal answer for it again. E to the negative 1/2 power gives me about 0.61. So my x value there is about 0.61. Okay, the next one, we've got log base 4 of x plus 3 equals 2. The log is already by itself. There's nothing in front of it, nothing at the end of it. We've just got log of this expression equals 2. So we're going to go ahead, because there's a constant over here, switch it to exponential form. So we have 4 raised to the second power equals what's inside the log, x plus 3. So that gives us 16 equals x plus 3. And then subtract 3, we get a value of 13. Okay, last example. You notice that we have two logs on the left side and we have a number on the right side. So before we get too into this and switching it to exponential form, I have to condense these logs first. If you have multiple logs on one side, condense them first. So this will become log base 2. We're multiplying this, so we're adding, so we're going to condense it using multiplication. So we have log base 2 of x times x minus 7 equals 3. Now switch it to exponential form. We've got 2 to the third power equals x times x minus 7. And you probably want to go ahead and distribute that x. So that gives us 8 equals x squared minus 7x. And then let's get everything to one side and try factoring. So I'm going to subtract the 8. Move my paper up here a little bit. So I'm going to subtract the 8. So we have 0 equals x squared minus 7x minus 8. And this is another one where we have to factor and use the zero product property. So we get x minus 8 and x plus 1. So when I set those equal to 0, I get solutions of positive 8 and negative 1. Now remember what we said earlier about making sure that you don't get a negative inside the log. Will either of these produce a negative when we plug it inside the argument of the log? Take the 8. We get 8 here, 8 minus 7, no problem, that's a positive number. Take the negative 1. If you plug in negative 1 here, you immediately have a negative inside the log. Same thing here, you'd have a negative 8 inside the log when you substitute the negative 1. So we're going to throw that out, and our only solution is going to be x equals 8. So pay attention when doing the homework to your numbers and just make sure none of the numbers, if you were to plug them into the original log equation, which give you a negative inside the log. And if they do, throw those answers out.